Hello, analysts. The noise you're hearing is my cat climbing the bed that I've put on its side to free up space for this recording studio. The purpose of this file upload is I'm going to talk through some of the homework problems that I've assigned and I will not be collecting. So let's go ahead and get started. So I guess I'll start at the start. Let's start with, homework 2.3.1 on monotone convergence. So the first item in that homework is theorem 2.3.7, monotone convergence part 2, which says the following: let A sub n be a too many screens. Be a decreasing be decreasing and bounded below I want to erase that. How do I erase it? Okay. Let A sub n be decreasing and bounded below then let A be the infimum of the set of all things that look like A sub n, where n is in n, then A sub n converges to A. So there's the theorem. Let's compose a proof. So start with the setup. We need to let A sub n be decreasing and bounded below. We need to let A be the infimum of the set of all things that look like A sub n, where n is in n. We want to show, I think I'm going to follow the convention of writing the want to show in a slightly different color. Nope, I don't want to highlight it. I want to show that A sub n converges to A. And, well, this is an epsilon n argument that I'm going to come up with, so there's like a preordained framework that these things kind of always follow. So let's consider any epsilon bigger than 0. There's the standard starting line. Now I need to come up with a choice of big N. Well, so let's see. Because A is the infimum of the set of all things that look like A sub n, where n is in n, there is some element of the set there is some element of that set. So there's some A sub big N, right? I want to come up with a big N, so there's my big N in the set of all A sub n such that n is in n. such that A plus epsilon. So the idea is A is the greatest lower bound. So A plus epsilon is not a lower bound. So there's something in the set which is less than A plus epsilon. So I've come up with my choice of big N. Now that I've come up with big N, I should consider any little n bigger than this big N. Then as A sub n is decreasing, A sub n is less than A sub big N is less than A plus epsilon. As A is a lower bound on the set of all things that look like A sub n, there's another fact that I see. I see that A is less than or equal to A sub n, because right, it's a lower bound, and well, certainly A minus epsilon is less than A because A is positive. Putting this all together, A minus epsilon is less than A sub n is less than A plus epsilon. So, there is an edge of this page. Okay, that's good to know. So what do I conclude? I conclude that the absolute value, zoom in a little bit, but hey, that's exactly what we wanted to show. So what can I conclude? I conclude that thus, for every epsilon bigger than 0, because I started by considering any epsilon bigger than 0, there exists some choice of big N. I came up with a choice of big N, such that for all little n bigger than big N, because I considered any little n bigger than big N, whatever conclusion I came up with holds under these conditions, absolute value of A sub n minus A is less than epsilon. But hey, look at what that is. That's exactly the definition of the limit. So A sub n converges to A as we claimed. Wonderful. I'm going to put it on pause for now. Okay, and I'm back. You didn't notice that I left, but it's been an hour or so. I walked the dogs. Let's continue going through the homework. Next page. Good. Yeah, there we go. I should start at the top of the page. So the next thing to talk about is, sorry, I'm trying to multitask. Okay. So the next homework item was the following. Corollary 2.3.8, which claims a decreasing sequence which does not converge, diverges, to minus infinity. So let's prove it. Poof. All right, so start it by declaring all the assumptions. It doesn't matter what you call the sequence, but I'll use the same name as suggested in the notes. A sub n be a decreasing sequence. Which does not converge. And just like before, I'll use a different color. I don't remember if I used blue. What do I want to show? I want to show that A sub n diverges. I already know that, though, because it doesn't converge. I want to show it diverges to minus infinity. And maybe it's worth elaborating on that somewhat. Let's remember what it means to diverge to minus infinity. So what do I really want to show? I want to show that for every choice of big M, there exists a choice of big N such that for our little n bigger than big N, A sub little n is less than M. So no matter how negative M I want the sequence to be, the sequence will become that negative, and it will stay that negative. So let's prove. Let us prove. So if that's what I want to show, first line should be consider any big M. I need to show all that. So the next thing I need to do is I need to come up. Oop. Looks like it's time for class to begin. Whatever that means. Well, what it means is there's an office hour, and, well, I am holding an office hour as I speak. No one's in the office hour right now. Consider any big M. I need to come up with a choice of big M. What do I know? I know that this sequence does not converge. And how am I going to come up with this choice of big N? I'm going to show that big M is not a lower bound on the sequence. So let's try to do that. So let's see. If big M were a lower bound on the sequence, then in particular, A sub n would be decreasing and bounded below. Oh, can I write off the edge? I can. That's interesting. So because A sub n is decreasing and bounded below by monotone convergence, A sub n converges. Contradicting, comma, contradicting the assumption that A sub n diverges. Thus, M is not a lower bound. Nice. Okay, so M is not a lower bound. What can I conclude from that? Because M is not a lower bound, there exists some big N in the natural numbers with A sub big N less than m. Sorry, I'm going over the edge of the page, which is bad form, but I hope you can forgive me. So there's my choice of big N. All right, what was my goal? I considered any big M. I've now cooked up a choice of big M. Sorry, I'm pointing to this and then to that. Now, well, I should consider any little n bigger than big N. So let's zoom in. Consider any little n bigger than big N. Because a sub n is decreasing, that means that a sub little n is less than or equal to a sub big N, which by assumption, well, not by assumption, because of the preceding line, is less than big M. Thus, a sub little n is less than big M. And now let's tie it all together. So what have we done? Well, let's read what we did. We started by considering any big M. So thus, for any big M, we cooked up a choice of big N. There is some big N, so that the next thing we did is we considered any little n bigger than big N, such that for any little n bigger than big N, what did we conclude? We concluded that a sub n is less than m. That's exactly the definition of what it means to diverge to infinity. Therefore, a sub n, sorry, I said infinity when I meant the opposite. A sub n diverges to minus infinity, as we claimed. Nice. Cool. So, hopefully you guys went through the proof of that already, and came up with a proof pretty similar to that. There's one more exercise on the next page, apparently. So, the next exercise guides you through a claim that a sequence of partial sums converges. So I'm going to go to the next page. So I guess this is problem 3 on 2.3.1. So let's let S sub n be the sequence given by the formula, the sum from k equals 1 up to n of 1 over k squared. Claim. Claim. S sub n, this sequence, converges. I'm not going to make any attempt to see where it converges. I just want to show that it converges. And how will I do that? We'll do that by showing that the sequence is increasing and bounded above. And, well, let's do it. So first, we will show that Sn is increasing. How will we do that? Well, I need to show that for every natural number n, S sub n plus 1 is bigger than or equal to S sub n. And that's pretty straightforward. So let's consider any n in n. Now I'm in my Colab Ultra meeting right now. Consider any n in n. Then I want to show that S sub n plus 1 is bigger than S sub n. So let's write down S sub n plus 1. So by the very definition of the sequence, this is the sum from k equals 1 to n plus 1 of 1 over k squared by the definition of the sequence Sn. Well, but what does this sort of summation mean? That means 1 plus 1 over 2 squared. You know, that's really, I don't care that that number is 1. I care that number is 1 over 1 squared, which is 1, plus 1 over 3 squared plus dot 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 dot, plus 1 over n squared plus 1 over n plus 1 squared by expanding. And, well, a thing to look at now is, check out just that much. That much looks like a partial sum. So that's equal to S sub n plus 1 over n plus 1, parenthesis, parenthesis, squared, again, by the definition of S sub n. Okay, now let's just wrap it up. I want to show that this sucker is increasing. That's bigger than S sub n because 1 over n plus 1 squared is bigger than 0. Oh, cool. So, thus, S sub n is increasing. So, if I could then show that this sequence is bounded above, the sequence S sub n is bounded above, I could apply monotone convergence and get the desired result. I can't do that immediately, but there's a suggested item 2. Item 2, claim. For all n in n, 1 over n plus 1, parenthesis, parenthesis, square, is less than 2 over n plus 1, parenthesis, parenthesis, n plus 2. And I've given you no reason to believe that that's important, but we'll go ahead and check that that is indeed the case. And, well, here's how I'll do it. So this white space to the right is like scratch walk. So let's do some scratch walk. So here's what I want to show. 1 over n plus 1 squared is less than, and I'll put a question mark there because I want to show this, 2 over n plus 1 n plus 2. So what I'm going to do is I'm going to manipulate both sides, and then the actual proof will be the reverse of whatever it is that I wind up writing down. So I guess cross multiply first. That'll give me n plus 1, n plus 2, and it looks like I'm multiplying only by positive things, so there's no worry about flipping this inequality. By some cancellation, that will give me n plus 2 is less than, and I need to remember to put these question marks there. I put them there for a reason. 2 times n plus 1, foiling out the right-hand side, canceling all the stuff I can. Oh, cool. So there's all I need to know. Why is that true? That's true because n is a natural number, so n is positive. So the actual proof is going to go through these steps, so keep them in your head, but I'll do them in the opposite order. So, well, I guess I should start, I need to prove something is true for every n and n. So let's let n be an element n be an element of big N. if you want to prove something is true for every natural number n, you better consider any natural number n. And it looks like the only thing that I need to worry about, all I need to make this proof work, is the fact that n is bigger than 0. So over here, multiplying something that's bigger than 0 by 2 makes it bigger. So little n is less than 2n. By adding 2, I get n plus 2 is less than 2n plus 2. And by simplifying, that's 2 times n plus 1. So maybe I'll even give myself some space by adding 2 and simplifying. Yeah, let's be more specific than simplifying. I have the ability to erase. And factoring. Okay, well, I can't erase that anymore. But I can do this. There, that comma isn't there anymore. All right, by adding 2 and factoring, I get that conclusion. To go from here to there, looks like I need to multiply both sides by n plus 1. So let's see, since n plus 1 is bigger than 0, we may multiply both sides by n plus 1 to get n plus 1 times n plus 2 is less than 2 times n plus 1 quantity squared. Good. So that gets me to there. How do I go from there to there? Well, I just need to do some division. By, well, let's see, maybe this is a weird thing to write, but by cross-dividing, and everything is positive, so I can, 1 over n plus 1 squared is less than 2 over n plus 1 times n plus 2. And now maybe a concluding sentence. Thus, for all n in n, 1 over n plus 1 parenthesis squared is less than 2 over n plus 1 n plus 2. Cool. So there's part 2 of this argument done. Step 3 indicates that you should use induction and item 2 to prove that for all n, s sub n is less than 2 minus 2 over n plus 1. Well, let's do it. 3. Claim. For all n in n, s sub n is less than or equal to 2 minus 2 over n plus 1. I think I might prove that it's in fact strictly less than, but that would be okay too. Proving a result stronger than what you need is never necessarily a bad thing. All right, well, let's go through and do it. Proceeding by induction. When n equals 1, s sub n is equal to 1 over 1 squared is equal to 1. and 2 minus 2 over n plus 1 is equal to 2 minus 2 over 2, which is 1. Thus, S sub n is less than or equal to 2 minus 2 over n plus 1, at least when n equals 1. Next, the inductive step. So the inductive step, I need to prove that if the claim holds for a number n, no matter what n is, then it holds for the next number. So let's consider any n in the natural numbers. Let's suppose S sub n is less than or equal to 2 minus 2 over n plus 1. We must show, well, this is like a want to show statement, so blue. Want to show S sub n plus 1 is less than or equal to 2 minus 2 over increment n by 1 on this side 2, n plus 2. There's what I want to show. And the place where I will begin is I'll begin with S sub n plus 1. I'll begin with this side. Well, S sub n plus 1, well, let's see, I've already checked that that is equal to S sub n plus 1 over n plus 1 squared, as we observed in step 1. That is now less than or equal to 2 minus 2 over n plus 1 plus 1 over n plus 1 parenthesis squared by our inductive assumption. Nice. And, well, even just, right, there's no guarantee that these are reasonable moves. This is just a decent autopilot thing to do. I saw something that I could use the inductive assumption on, so I used it. So let's keep on going. Yeah, still no one in the session. So I know something about this. Let's use that I know something about that. So that is strictly less than? Less than or equal to. So I'm leaving this alone. 2 minus 2 over n plus 1 plus 2 over n plus 1 n plus 2. And that was step 2 by step 2. And now the proof will boil down to just arithmetic. So look at what the want to show is. There's the want to show. Presumably you've written it down already, so I don't need to remind you. I see a 2 there. I see a 2 here. That makes me happy. I see 2 minus some stuff. I see 2 minus some stuff. Let's just see what the stuff that we need to subtract is. So I'll leave the 2 alone because the 2 makes me happy. 2 plus, I see a fraction and a fraction, so let's combine them into 1. So I'll put the minus 2 up there. N plus 2 plus 2 over n plus 1, parenthesis, parenthesis, n plus 2 by algebra. All right, well, let's keep on simplifying. That's 2 plus something divided by n plus 1 times n plus 2 minus 2n minus 2 times 2 is 4 plus 2. Once again, just simplifying more algebra. 2 plus, let's see, 4, negative 4 plus 2 is minus 2. Minus 2n minus 2 all over n plus 1, n plus 2. Let's go ahead and just pull out that negative 2. So that's 2 minus 2 times n plus 1 all over n plus 1, n plus 2 equals 2 minus 2 over n plus 2 by simplifying. All right, so for those of you who have lost sight of the forest for the trees, go back to the want to show. Is that the thing we wanted to show? It sure is. Unfortunately, I now need to go to the next page, but hey, that happens. Thus, by induction, comma, S sub n is less than or equal to 2 minus 2 over n plus 1 for all n in n. Nice. All right, let's item 4. Deduce that 2 is an upper bound. 4. Claim 2 is an upper bound for this sequence S sub n. So what does it mean to be an upper bound? It means that for every natural number n, S sub n is less than or equal to 2. So I'll include that want to show, even though, well, you already see, hopefully, the intent is that at this point you already see what the proof is. So we want to show for all n in n, S sub n is less than or equal to 2. So let's do that. So I want to show something is true for every natural number n. So let's consider any little n in the set of natural numbers. No, I don't want that to be my next line. By the thing we just proved, claim 3, S sub n is less than or equal to 2 minus 2 over n plus 1. So that's 2 minus some stuff. When you minus some stuff that's positive, you make the thing smaller. So because, in fact, you know what? I'm going to rearrange this just a little bit. Okay, so apparently you can only erase so far back? Ah, okay. Then S sub n is less than or equal to 2 minus 2 over n plus 1 by claim 3. That in turn is less than 2. because 2 over n plus 1 is bigger than 0. Oh, nice. That's all I needed. So I can prove something is true for any natural number n. So that means for any n in n, s sub n, is in fact strictly less than 2, but I'll be happy enough with less than or equal to 2. 2 is an upper bound. Well, and now, well, I'm basically done. I want to show that this sucker converges. 5. Claim. S sub n converges. Well, let's do that. By item 1, S sub n is increasing. By item 2, nope, not item 2, by item 4, S sub n is bounded above. So, by monotone convergence, S sub n converges. And notice, I have no idea what the limit is. Part of the point of this example is that's one of the powers of monotone convergence. You don't need to have a guess. There are techniques which are outside of the scope of this class, which conclude that the limit of this sequence is pi squared over 6. The probably most straightforward technique passes through the setting of Taylor series. You write down a Taylor series for, I think, arc cotangent, and you plug in 1, and you see what the sequence is. And because it wouldn't be 1, it would be 1/2. Because the inverse cosine of 1/2 is pi over 6, you get the result. But that's not what the point of this exercise was. The point of this exercise was just, it exists. If you want to approximate what the series is, you can. You can add up the first, 10,000 1 over a square number, and you'll get an estimate. Cool. So that completes one of the homeworks that I want to talk about. The next one is the section on cardinality. And let's do that. So let's go into section 2.4.1. The first item on the homework was claim. For any set A, the size of A is equal to the size of A. Well, so let's unravel the things we want to show. So I want to show, what does it mean for two sets to have the same size? It means that the first of them has size less than or equal to the size of the second, and the size of the second, but that's the same as the first, is less than or equal to the size of the first. There's what I need to show. And how do you prove that cardinality inequality like that? How do you show that the size of A is less than or equal to the size of A? Well, you need to find an injective function. So there's only one function I know from a set to itself that if I don't know anything about the set, and that's the identity map. So let's prove. Let A be a set. And now I need to come up with this function. So let's define f from A to itself by some rule. Let's define it by the rule sending f of a to itself. If I don't know anything about the set, I can't write down a complicated formula. I can't like square or add one or any stuff like that. I don't know if A knows what it means to add one. All right, well, I need this function to be one-to-one. Want to show f is 1 to 1. Well, how do you show something as 1 to 1? Well, let's consider any a comma b in big A. Let's suppose f of A is equal to f of B. If I want to show the sucker as 1 to 1, then I need to show A equals B. Well, let's see. By the definition of f, the assumption f of A is equal to f of B means A equals B. Oh wait, that's what I wanted to show. Thus, for all A and B in A, if the assumption is true, then the conclusion is true. If f of A equals f of B, then A equals B. F is 1 to 1. Ooh, someone's joining the office hour. Pause. Okay, the person who is trying to join seems to have not been able to. So I will keep my eye on that. I will probably stop again, but except for the fact that I'll point it out by saying something like this, you'll never know. So let's continue going through this bit of homework. So there's a difficulty in using the one computer screen for everything if you're disorganized like me. All right, so the next thing to prove, 2, claim. For any sets A, B, and C, if the size of A equals the size of B, and the size of B equals the size of C, then the size of A equals the size of C. And this is another one that will be really straightforward. This particular homework was supposed to be pretty light, with the intent that no intent. Let's just not worry about that. You're not here to think about that. You're here to think about how to prove the homework problems. Sorry, I'm getting a little bit sleepy, which usually happens about now, but I'm usually in class and I'm not sitting down, so it's easier to stay awake. Well, let's write down the assumptions. So let's let A, B, and C be sets. Let's assume size of A less than or equal to size of B. Oh, no, not less than or equal to. That will be something that gets used soon. Size of A equals size of B, and size of B equals size of C. Let's write down what those things mean. Or maybe some want to shows are in order. Want to show size of A equals size of C. In other words, in essence, in est, size of A is less than or equal to the size of C, and size of C is less than or equal to the size of A. They're the things that we need to show. And in order to show those things, let's just unravel the assumptions. So let's see, because size of A equals the size of B, we know that size of A less than or equal to size of B, and I'm going to, I think, indicate each of the following claims with some symbols. So this will be item 1. Size of B is less than or equal to the size of A. There's item 2. They should have an and between them. And you don't need a comma if there's an and right there. I am an advocate of the Oxford comma, but this is not a place for, this is not an Oxford comma. Because size of B equals size of A, equals size of C, I conclude some things. I can conclude that the size of B is less than or equal to the size of C. That's item 3. And size of C less than or equal to the size of B. There's item 4. Now let's just combine these things together. By 1 and I'm going to leave myself some space. By 1, I know that the size of A is less than or equal to the size of B. And I know that the size of B is less than or equal to the size of C. Let's just keep track of which one tells me that. 3. By 3, I know that the size of B is less than or equal to the size of C. So, you have the notes in front of you. I, however, just have the homework list, which tells me which item to use. So, by claim 2 of prop 2.4.3, we conclude size of A is less than or equal to the size of C. So that claim from this proposition is the one that tells you that inequality, that being smaller than is a transitive relation. And the next argument is basically the exact same, so I'll shorten it. Similarly, using 4 and 2. So let's just read them off in our heads at least. 4 tells me that size of C is less than or equal to size of B. Size of B is less than or equal to size of A. So the exact same argument will tell me size of C is less than or equal to the size of A. All right, so we're done. Because size of C less than or equal to size of A and size of A less than or equal to size of C, we conclude size of C equals size of A as we claimed. Wonderful. So The next item in the homework was a group walk. So I'm going to go ahead and stop this recording now, and I'll post another one for the group walk. Talk to you later.